So the damping coefficient actually comes from these systems that look like, well, that are drawn like this. So these are called spring mass dashpot systems. This is exactly the suspension system of your car. Right, so I don't know how many of you have ever taken the time to have a look at the suspension system of a car, but you may be familiar with the idea that your car has a wheel and that there is a very massive steel spring that connects the car. I'm kind of exaggerating the scale here, but it connects the car to the chassis, right? So there's this big metal spring that connects, that kind of connects the car to the chassis. Now, if you just had that spring, if you were to go over a bumpy road, the car would be going like this all the time. And that's that second order response, right? So the reason why we have shock absorbers, so in your car, the shock absorber, I mean, typically it sits kind of behind or inside the spring, and that shock absorber is this dashpot. So this spring corresponds to the spring of your car. The mass actually corresponds to kind of the big mass of the car that's on top of that spring. And so like in statics, if you're doing dynamic problems like mechanical problems, they have that top as just being like a stationary, that's like Earth, right? And so if you were to pull down on this mass and let it go, it would do that in terms of its position, right? So if you had a little arrow and a piece of tape or paper or something on there, if you had that like with a pen, like a lie detector machine, if that was exactly what that shape would look like. If you pulled the spring and you let it go, and if you go and do the force balance on that, you'll notice that becomes a first order or a second order differential equation. Right, so basically the standard way of analyzing this is that you've got like a Hooke's law spring, you've got the mass, and so without the damper, if you had an ideal spring, if you pulled the spring down and let it go, it would oscillate sinusoidally forever. It would be like a pendulum, right? But if you have the dashpot there, that's removing energy from the system, and it'll eventually go smaller and smaller. And so that's a literal physical piece of kit that you can say would exhibit second order underdamped response. Now you can increase the damping, right? So you can increase the damping on this dashpot until such a point where if you pull it out and you let it go, it just does that second order response. So it does exactly the second order overdamped response, because the damper is damping enough. And again, we're assuming an ideal damper where only dynamic friction is in play, because obviously there's a transition from dynamic to static friction. So technically what happens is there will be a point at which the force is not large enough to overcome friction, which will happen. So technically, when I'm saying overdamped, the ideal overdamped response will be like asymptotic to the original position, but the true response will kind of run out of steam and stop before it gets to the original position because there's friction. I hope that satisfies you. Yeah. So I mean, you can just as an aside, try and analyze that system dynamically. It's the forces of motion, or the equations of motion. There's nothing special in that. So if you just assume that the dashpot is a friction device, so it resists, it has a force proportional to the velocity, and the spring is a Hooke spring, you can model that system, you can model the position of that mass very, very accurately. Another place where you can see this kind of oscillation, another really nice little physical system is in a pendulum that, a pendulum that doesn't swing very far approximates very well as a linear system as well. And so if you have a pendulum with no resistance, that'll just like move sinusoidally. If you have a pendulum with a little bit of friction, that again applies a torque at this point. So this is a pendulum. It's fixed at that point, and this part swings. And so if there's a little bit of friction at the connection point, that will exert a torque proportional to the angular velocity of the pendulum. Right, so that's how friction works, you remember. So like friction works like it opposes motion. And so if you have that kind of friction, then the pendulum, like all real pendulums, will eventually stop. And that's, again, if you plot the motion of the pendulum, you'll get a second order response. So it's very real.